you are. If you have come to the webinar Grid Edge Solutions to Accelerate Renewable Deployment in Islands and Remote Communities, you have come to the right place. We will wait for a minute or so before we start the webinar as such. And in the meantime, I'll do a few housekeeping announcements. Firstly, just to let you know that you will receive the video recording and the slides delivered during this presentation. So fear not, we'll send them to you by email and probably early next week. And also, I'd like to let you know that you can ask questions during this webinar. So if it's the first time you come to an ATA Insights webinar, you can see at the bottom of the screen there is a Q&A or questions and answers box, and whilst Hamide and Pablo are delivering their presentations, you can pose your questions there. I'd also, we have a tradition here at ATA Insights that we ask everyone in the audience to post where they're joining from. So I am here in Madrid, Spain, and so is my colleague Manuel, although we're in different locations because, everyone knows what's going on now, right? Just before we start, I'd like to make an announcement on behalf of Hitachi ABB Power Grids. So on July 1st, Hitachi Ltd and ABB Ltd completed the formation of Hitachi ABB Power Grids Ltd. So this joint venture brings together two highly respected companies to create a new global power leader. That's just so you know that who will be addressing you today. So I think we've given enough grace time to those viewers who might have been lagging a little bit behind. So I think it's probably as good a time as any to start. So before we start, could you, Manuel, could you stop sharing the screen? And I'll get each of the speakers to briefly introduce themselves. So Hamida, could you please introduce yourself briefly in a couple of sentences?
Sure, thank you, Carlos. I'm Hamide Bitaraf, the Senior Advisor in Grid Edge Solutions at Hitachi ABB Power Grids. And I have a global role, so I work with customers who are interested in Grid Edge Solutions, and we provide different consulting and advisory services to help them through their renewable investments.
Thank you very much, Hamida. And Pablo, please, could you introduce yourself and also get ready to deliver your presentation, please?
For sure. So thank you, Carlos, and thank you, Hamide. So my name is Pablo Astorga. I'm the regional sales manager for a business we call Grid Edge Solutions at ABB, Hitachi ABB Power Grids, that focuses on what we will deliver today, integrating renewables, providing power quality solutions for remote locations and utilities. Based in Madrid, same as Carlos, and we will start shortly with the presentation. So allow me to present it.
Yeah, I can see it now. And
very good.
There we go. Now it's full screen. Perfect. Please, Pablo, over to you.
Perfect. So thank you again, Carlos, and thanks everybody for joining this webinar on Grid Edge Solutions to Accelerate Renewable Deployment in Island and Remote Locations. We have structured this presentation in basically two blocks. I will drive the first one, which will focus on context, some market drivers, what are the challenges that we see in these kind of scenarios, and also what are the types of solutions. And of course, we'll also talk about real life examples that illustrate what I just explained. Then we will move on to the second part, which will be driven by Hamide, in which we will actually look at specific business case analysis and more detail into real life situations that explain how these systems actually work. And in between both blocks and also towards the end, we will have some polls to gather a little bit of your insights and feelings about what you see in this market. So without further ado, let me start by stating that grid edge solutions is what we refer to as a combination of different technologies that help us address the challenges and the needs of island utilities and remote locations. We will speak a bit more about that later on during the presentation, but it's important to understand what are the market drivers behind these market needs or these customers, right? So on the one hand, we see a clear need for more affordable electricity. In many locations, the imported fuel makes electricity extremely expensive, and particularly when compared to the mainland. So that is a challenge in many places. In a way, some of the grids, particularly in many island utilities and also remote locations, are maybe not as strong as they should be. So there's a need for grid stability, power quality improvements, and this is also something that we see as a strong need from many utilities and other types of customers in this kind of projects. And also, of course, we see a very clear trend in their deployment of renewable energy in the form of solar or wind. That has been a clear trend over the last decade or more, depending on the location. And this, of course, brings a lot of opportunities, also some challenges. And between those two, we try to provide solutions that actually help address those challenges and increase the opportunities. So, of course, allowing an island utility or a remote location to become energy independent, to increase power quality, to reduce the cost of electricity, are all, and of course, to reduce the carbon footprint and maximize the penetration of renewables are all clear goals that maybe were challenging to achieve only a few years ago or maybe a decade ago, but are now very, very feasible with some of the technologies that we will discuss today. So we will talk about the technologies, but we will also talk about the numbers, and Hamide will actually drive us through a very, very complete analysis that shows how these projects actually work, not only from a technical perspective. So with all this in mind, it's probably obvious that or logical that many island nations around the world have actually developed policy and regulation around the deployment of renewable energy. So as you can see on the left of the slide and the chart, there's many cases in which some targets have been defined for maybe a penetration of renewable energy between 10 and 20% or higher, right? We are taking here a snapshot of the targets by 2030, which is just around the corner in energy terms. But you can also see that for that same time frame, many island nations have actually decided that they want to source their electricity from 70 to 100% renewable sources. And that is really a very bold goal, but also a feasible goal. It's feasible when one plans appropriately and when one actually deploys the right technologies. Of course, this is the case everywhere. So you can see on the right-hand side of the chart a map that shows again a little bit of a picture of where policy and regulation is today in place or about to be in place implementing such goals. We see a lot of activity in the Caribbean. We see a lot of activity in the Indian Ocean and of course in the Pacific Ocean and as well in the Atlantic. So pretty much everywhere. We will discuss in a bit more detail some cases that we see around the globe. And one thing maybe that is important to highlight, this is here we're talking about policy and regulation in these charts, but there's in many cases a clear drive from customers that even in the absence of policy and regulation, they see a need, they see a business case, and they end up deploying projects by themselves, as we will see in more detail later on. So now that these goals can be achieved, but they cannot be achieved by a simple technology alone. So this is why we talk about grid edge solutions. Grid edge solutions is, in our view at least, a combination of different elements. If we start at the bottom of this slide, we see that we are obviously combining different assets, maybe solar PV or wind, and of course energy storage, maybe in the form of batteries or the like. And these are physical assets, hardware assets that are deployed in a particular system, right? But of course, these assets have all of their advantages, depending on the location, depending on the conditions, but they do not magically work together, right? So we need a layer of intelligence above that is starting to refer to control and automation that allows those physical assets to then be combined and operated together. So this is what we call the control or automation layer. And this allows us to do a lot of interesting things, like for instance, make sure that the overall system complies with the grid code, make sure that we manage properly the feeders and the loads that we are trying to serve with these renewables or the existing fossil fuel-based generation or with the energy storage device themselves. So there is a level of automation and intelligence that we necessarily need to deploy in order to make sure that these assets are not individually seen, but that they are working collectively as a system. But even beyond that, and obviously you might notice that the higher we go in this slide, the more advanced, the more sophisticated technologies come into place. We might then start talking about supervisory control and data acquisition systems, SCADA systems, just for data acquisition, understanding what's happening in the system, being able to take action on some of the things that might be happening. And of course, at some level above, we might want to use cloud-based solutions for data access monitoring and control in remote systems. And very, very interestingly, at the very top of this chain, we see what we call applications, which could be a very good fit for many cases. For instance, if we need to do forecast, production forecast or optimization of the planning. So if you imagine you have a combination of assets that could involve solar PV or energy storage in form of a battery or wind, there might be technical reasons why we might stabilize the system in a certain way, but there could be other reasons that are maybe not technical in how we actually manage the system. Do we want to store the excess energy of the solar PV in the battery for use at a later stage, or do we actually want to sell it right now or put it into the grid right now? There are different strategies and combinations that can be actually performed. And this happens with what I would call advanced optimization software, which is very sophisticated part of the suite that we call when we refer to grid edge solutions. Now, with these technologies combined in whatever form, we can actually do many different things. So very important when we're trying to deploy a system and decide what we're doing is trying to understand what is the challenge that we're actually solving. We like to say that very often battery energy storage systems can be looked at as a Swiss Army knife, so a tool that can do many different things. And it's important to understand what are we actually trying to solve. With a battery energy storage system, we can actually perform, as you can see on the slide, frequency regulation services. We can, of course, also provide peak shaving, which is extremely useful in many cases. We can help with spinning reserve and provide directly spinning reserve and therefore release the use that is currently being done by maybe some generators with the associated cost. And of course, we can do many other things as well. Seamless transition between on and off grid modes, of course, maximization of the renewable energy integration. So there's a number of different functionalities that can be performed with the same technology. So it's very important to understand what is the challenge that we have and what are we trying to achieve so that we can then properly design and size a system to overcome that challenge and run this asset in an optimized manner. In general, what we see with island utilities and remote communities is that we see a drive for, as I was saying at the beginning, for grid stability, power quality. We will see some examples in a couple of minutes, whether it's islands that are hit by hurricanes or if there is, in some cases, maybe some instability coming from the introduction of renewable energy, or simply difference in peak loads from different seasons. All of these are challenges that, of course, pose a problem for the operator of the system, and they can be solved with the same technology. But it's very important to understand upfront what are we actually trying to solve when we deploy a system, because that is the only way that we can then size and optimally design one. One thing that is important to highlight is that while there is not always a need for renewables to already be there before we deploy battery energy storage systems, it is common that there are already renewables in place. It's also common that the battery energy storage systems can be deployed to make the systems renewable ready, as we call them. We will explain this with a very graphical example in a couple of minutes. I just want to make the point, excuse me, that it's very often the case that it makes sense to start maybe with a battery energy storage system that provides power quality, that increases the system reliability, and then maybe later on start deploying renewables to the rate that is maybe expected to achieve those targets that we mentioned in the earlier slide. Now, to provide a more visual representation of what we are talking about, so we're talking about the functionalities, we're talking about the market drives and needs. How do the systems actually look like? So we thought it might be worth showing how we actually envision them in Hitachi ABB Power Grids. There's different ways to approach a project, but essentially we split it in two different types. So one is what we call integrated, in which a single enclosure houses everything from automation to power electronics, electrical, AC and DC equipment, and batteries, of course. And then there is the other route, which we call modular, which for larger projects looks at outdoor equipment on the power electronic side and on the electrical side, on the transformer side, and then containerized solutions for the batteries themselves that need the very special conditions when it comes to temperature, humidity, and the like. So with this in mind, it's very important to say as well that regardless of what solution size and approach one takes, the functionalities can be achieved by both, and also they are important to be understood up front, or else there is a risk of obviously not optimally designing a system properly. So with that said, let's go into something a bit more practical. So let's talk about specific cases, of course, related to islands and remote locations that we have seen, and where we have seen that the challenges were there and the solutions came through this type of technology. So let's take first an example in the Caribbean. This is in Grand Bahamas. So the Grand Bahama Power Corporation had some issues with power quality and grid stability. And this is primarily driven by one of their main industrial customers, which is the port. And in the port, you typically have a number of cranes, and those cranes are quite demanding when there's a lot of traffic, and also they are driving some peaks. So of course, if the crane is moving and loading containers and then dropping them off, and then maybe moving another container, that is a lot of peaks and quite some stress into the system. So here we have a case in which, without renewables in place, the introduction of a BESS, of battery energy storage system, make perfect sense for two reasons. One is solving the issues that were there already, that were putting some stress on the existing generators. In these cases, you can see on the slide, there were diesel generators, improving power quality, system stability, and at the same time, as I mentioned earlier as well, making the system renewable ready. So the system would have struggled to incorporate renewables with the existing power quality issues if it weren't for the system that it is now deployed. And now we have actually, after having deployed the system, seen a couple of benefits that are real, that have been there. One is that after a hurricane hit the island very hard last summer, with a BESS in place, the recovery of the full electric system was much faster than in the past. It was also done in a gradual manner and with much more higher, power quality. So this is an example also of how these systems can help recover from unforeseen or unplanned situations. And of course, the second one is that now there is an introduction happening of renewable energy, in this case PV, that is now being introduced into the system in a safe, stable manner without any power quality issues. So this is an example in which a grid edge solution, in this case, a combination of a battery system and automation, no renewables at the very beginning, helps solve the challenges of this utility, which were around power quality. Let's move on to a different example. This one is in South Africa. Robben Island is a small island off the coast of Cape Town in South Africa. It is a small system. It is, as of today, a World Heritage tourism attraction, and it has been traditionally run by diesel generators. And what we did a couple of years ago is we introduced a combination of not only the existing diesels, but also solar PV in the range of 600, as you can see, 600, 700 kilowatt peak, and then a battery system with 500 kilowatt of power rating and about 800 kilowatt hour of battery. And what we do with the combination of all these systems, and of course the automation layer that I mentioned that makes it all work together, is we're able to run the system purely on solar and battery throughout the day, and obviously only run the diesels whenever there's not sufficient renewable energy resource, in this case solar, and the battery is depleted. So if there is enough solar resource, then with that and the battery, we can run the system, managing the fluctuations coming from the solar. Whenever there is no more resource, or it's maybe coming close at night and maybe the battery is depleted, then at that point in time, we run the diesels. This allows us to run this system for more than 9 months on solar, which is a fantastic achievement. And during many times, like I said, most of the days, it runs without any diesel at all, which is a significant and a fantastic change versus the traditional operation of this system. Of course, this is all modular, so it can be expanded depending on the needs of the system. So it's a different case than the one before. Here, it was the introduction of renewables what drove the installation of that battery system. Same technology, slightly different application. Let's now take our journey to a slightly different place, Alaska. So as you can also see, different weather conditions and different environment. Backland and Deering are two very remote communities in Northwest Alaska. And what has been happening there is kind of similar to what we have seen in Robben Island, so operation based on diesel and the introduction of renewables. In this case, not only solar, but also wind in the ranges of power that you see on the slide, so in the hundreds of kilowatts. What we have been able to achieve with the system is a couple of things. On the one hand, these communities have achieved energy independence. They have reduced significantly their diesel consumption, which is extremely useful and helpful, particularly also when it comes to logistics in places that are not easily accessible in the winter. It's very good if one does not need to store the right quantity of diesel or buy it at the right time in the market. So it's very good to become energy independent, but it's interesting as well here that we are managing multiple resources that we're integrating. So it's not only solar and diesel and the battery as we saw earlier, it's also wind. So we can then take the benefits of the wind blowing maybe at night and the solar producing during the day. And the combination of all these assets, again, with this layer on top of automation and intelligence and control, is what makes a system be able to run in this particular case for several days in a row without any diesel at all. So very interesting case as well, again, in very different conditions as well when it comes to climate and environment around it. What we have next is an example in a very different location. So this is the island of Porto Santo in the Madeira archipelago in Portugal, so in the Atlantic Ocean. And here again, we have a different case. So we have already existing renewables on the island. We have a system that has some challenges in the sense that it's a tourist place as well. So in summer, the load has a big deviation versus maybe the winter load. So there's some challenges there when managing the grid and also, of course, the existing diesel generators could use some optimization when it comes to managing the unplanned issues that could happen in the grid. Hamide will explain actually in more detail with real data how the system responds to events that happen in the grid. But I think what's important to explain here is, on the one hand, that there is a big driver once again by, in this case, another utility that has renewables that is willing to grow that renewable energy mix, in this case, up to 30%, and that is also having some issues on the grid. There is an opportunity with this technology, grid edge solutions, to actually manage those challenges and get ready for further integration of renewables. So these are very different examples, as you can see. I hope it's clear that the technology that we use is the same, but the application that we use it for is different. So in some cases, we saw pure power quality issues in Grand Bahamas. We saw renewable energy integration in Robben Island. We saw also the integration of multiple sources of renewable energy in Alaska. And now we see here a combination of different aspects. What is important to note is that, and this is why we show on this slide in the map, is that the same technology can be achieved for many different functionalities, but also for many different regions, many different conditions. So the cold Alaska and the hot South Africa, for instance, to pick those two examples, or in islands and remote communities of any sort. And as you can see, it's deployed in the same fashion, right? So we might go for a fully integrated solution, a fully modular solution, but at the end of the day, same concept, showing the benefits of this technology and how they apply to the particular cases of each customer. So regardless of location, regardless of weather, regardless of size, we would approach it in the right way. What's important to understand is what is the challenge that is there and how do we try to solve it so we can do proper and optimal sizing. Now, with that said, we will move on into the first of our polls, and then Hamide will continue to go into the details of one of the business cases that we have presented.
Thank you very much, Pablo, for your presentation. So now, Manuel, you have the screen ready to start the poll. So right, so we just want to see if you're still with us. Hopefully, yes. I can see the first few answers. So give us your thoughts. So have you deployed any microgrid / energy storage projects so far? Let's give it a minute or so for the poll to be answered. And well, whilst you answer your poll, I'd like to remind you that we are definitely recording this session, and you'll get a recording of the session in a couple of days' time, and we'll also send you the slides. And also, well, for now, focus on answering the questions on the poll. But remember that you can also post questions on the questions and answers box. I can see that some of you have already posted some questions. So we'll, after Hamida's presentation, which will come just now, we will answer as many of them as possible. So, right, it seems that everyone who wanted to take part in the poll has taken part. Let's give it a few more seconds to see if anyone. There we go. So, right. Well, thank you very much for your for participating in this poll. So, as you can see, most like 3/4 of participants in this poll haven't yet installed a microgrid or storage project. So you're at the right place to learn. Then we have a second question here, which is, when are you planning to deploy your next microgrid or energy storage project? So as you can see the options there. You have next month, in the next 6 to 9 months, next year, or I don't know, just exploring for now. Let's give it a few seconds so everyone can take part. Right, so, well, it seems that you've got the hang of it now, so great, all right. So, Manuel, over to you if you want to continue. Hang on, just give me 1 second with this. And right, so I think we can start the polls now and allow Hamida to present. Manuel?
Yes, please. Go ahead.
Okay. So, Hamida, please, over
sure.
to you. The floor is yours.
Sure. Thank you, Carlos and Pablo. So let me share my screen. Okay, perfect. So can you see the screen now?
Yes, I can see the screen now.
Perfect. Okay, great. So I will continue the webinar from this point. And as Pablo mentioned, I will describe some measured operational data from our Porto Santo BESS project that we installed the BESS energy storage solutions for our customer EM. Then I will describe a business case for an island utility or remote community that has the target of reaching and achieving renewable goals and reducing the carbon emissions. And then I will go through a power system study, just a brief, just like 3 slides of each to show that how's the difference between system response before and after integration of energy storage. Okay, so here you can see the operational data for our Porto Santo BESS project through and the data acquisition is actually through the Hitachi ABB Power Grids Network Manager. So you can see the load for this 24-hour and also the 16 megawatt diesel generator that was operating. And then you will see the 2.25 megawatt of solar. Then we have the wind here. And the blue line is showing the BESS operation throughout this 24 hours of window. As you can see, the event that we are looking for this slide is high renewable penetration. So you can see during the day we had the increased penetration of renewables from solar. And what battery did was actually providing frequency support to the system so that it can stabilize the system and somehow sustain the frequency within the allowable margins. And the frequency is also shown in the graph below. So the BESS actually provided the frequency support and stabilized the grid during the high renewable contribution times. Okay, so the next slide is actually again related to our image BESS project for Porto Santo, and as you can see, it is related to a contingency of generator outage event. So what happened here is actually the time window is for 40 minutes, and you see the measured operational data for the frequency, and we had 3 generator outages during these events. You can see that the frequency has dropped through these events, and the battery responded for these generator outages. So the battery actually compensated the generator outage and provided the support for the frequency excursion and sustained the frequency within sustainable margins. So these are our real operational data from our Porto Santo project that we provided the best solutions for EM utility. EM is actually the utility that supports the islands of Madeira and Porto Santo. So let's move to the other chapter. So now I want to discuss a business case for an island utility. So I will discuss these businesses in the next 3 slides, and we will explore the investment options for battery and energy storage solutions and their impact on renewable contribution, lowering the cost of energy. And you know, the project time for this analysis is mainly like 20-year lifetime, as we have in this scenario. And the island has a goal to be more affordable, to have more affordable electricity, access to a stronger grid, and have more renewables. So these are the main 3 goals for the island. And the island has a peak load of 15 megawatt and actually is suffering from occasional voltage and frequency issues and have some power quality challenges. So you can see here that we have assumed some economic and cost data for the installation of a solar PV battery and also the BESS. And we have considered different scenarios to be analyzed in this business case. So we can see what is the payback time, what is IRR, what is the renewable penetration in each scenario. So the first scenario is actually the business as usual, which is the diesel only scenario. The next one is the renewable ready that will explore the benefits of adding energy storage and improving the power quality and also providing spinning reserve for additional for future renewable installation. And the last 2 are kind of evaluating the case that we have both renewables and energy storage in the island. Okay, so let's actually dig in more to the different scenarios that I just said, and then we will discuss the results. So here, the initial grid, as you can see in this in the base case, which is diesel only, is powered exclusively by diesel generators, and during the peak daytime, 8 of them needs to be on, and 1 of them needs to act as a reserve. And that one is shown is in the red diesel generator symbol. So from the base case, we add BESS to the system and we move to the renewable ready scenario. So what will happen here is that you'll notice that 2 of the generators are now off because the BESS can improve the fuel efficiency and also improve the power quality and also provide reserve in case of any generator outages. So battery is an important investment here because it can solve one of the challenges of the island to improve power quality. So when we move to the next scenario, which is the medium renewable scenario, we will add PV to the system to increase, to actually have renewable penetration in the island. And we could have considered adding wind, but usually solar is the more viable and practical in every island, but it could be either wind. There's no issue on that. So the medium renewable scenario includes a 10 megawatt solar here and a 6 megawatt and 5 megawatt hour of the BESS. And when we move to the high renewable case, we will add more renewables and energy storage to provide the required spinning reserve for the solar. And as you can see, during some sunny daylight hours, all the generators could be shut down. So this could be one of the, flashback to the Pablo, the case that Pablo mentioned on Robben Island, that one of our projects could operate 9 months of the month on renewables and energy storage. So this could be the case that when you have a high sunny daylights, you can turn off the diesels and only operate on renewables and energy storage. Okay, so let's move to the next slide, which demonstrate the final results for these scenarios. So as you can see, this was the base case that has power quality issues and there was no renewables. So the island was looking to increase the renewable penetration and also improve the power quality. So what happened in the renewable ready case, that we employed the battery solution. As you can see, this case has the strong return compared to the others of 27% IRR. And BESS is important for the island to actually to provide a reserve for the future renewable investment. And when we move to the medium renewable scenario, you can see that we have 20% of renewable penetration here, and the power quality is improved here. And we have also reduced the LCOE, which is the levelized cost of energy, by 13%. And by increasing the renewable penetration, you can see that the renewable contribution will be increased to 35%, but for sure that needs additional investment. So I can say each of these scenarios really depends on if there is any limit on the capital investment for the island, if there is any certain goal to meet for the renewable contribution, and if the island is planning, for example, to invest in renewables in 5 years or not just 1 year. So we can talk to the island utility or the remote committee for each of these scenarios and see which one is actually more appropriate to meet their goals. So let's look at actually the next analysis. So actually the island business case, we have already a white paper published on that. The 3 slides that I just showed to you. So we will share that with you after the webinar, so you can read through the white paper, which is I think an 8-page paper. And for the dynamic analysis, so let's move to the dynamic analysis of the grid edge solutions. So here we consider the hypothetical island, and we want to see what is the impact of BESS on the island utility before and after integration of this technology. And the study that I will present is actually based on one of our published papers that we can share the link with you afterwards. So as you can see, the island has a peak load of 13 megawatt and it has a crane on site. So it is dealing with power quality issues because crane is a dynamic load and it will create frequency fluctuations for the island. And the island is supplied by 5 diesel generators here and is planning to invest in a 4 megawatt wind farm. So and is also have some protection system and requires some rampart control for the future wind investment. So what are the best applications that the utility is looking for in this case? So in this case, the utility is looking to get the benefits of installing a 3 megawatt and 1.5 megawatt hour energy storage and achieve the goals of ensuring a stable operation for the island grid and support the frequency and voltage through any contingencies, and also provide ramp rate control and improve the power quality issues. I will discuss the simulation of the dynamic analysis for two contingencies, which are load step change and also the generator trip events in the next two slides. So just a recap that what is the difference between like dynamic analysis and a business case. So as you see here, we are dealing with a contingency, and we look at a simulation in a time window of like a few seconds. So here we have simulated only 5 seconds, and the time resolution is in multi-second. But in the business case analysis that we deal with planning and actually optimal sizing of the grid edge solutions, we are looking at 20-year project lifetime and talking about payback time and IRR. So that's the main difference here. But we want to see really on the operational side, how does the energy storage react to any load step change or the generator outage trips. So you can see here that we have applied a 3 megawatt load step to the island, and the first row is actually showing you the simulations for before the BESS integration. So we have applied the 3 megawatt load step change, and the load was shed so that it will sustain the frequency within allowable limits. And you see the generator responses in this graph. So what will happen if we add the energy storage? As you see, if we add the energy storage will respond to that, to this contingency, and provide the prompt response to supply the additional load. And also it will reduce the frequency excursion here significantly and avoid the load shedding. So these are the main benefits of the integration of BESS in the load step changes. But on the other hand, if you compare the generator outage events, generator responses before and after BESS integration, you see that BESS has reduced the wear and tear on generators. So it has reduced the response from generators. So as a result, the BESS has reduced frequency deviation, avoid load shedding, and reduce the wear and tear on generators, and also provide ramp rate control and for any future renewable investment. So let's move to the next contingency that we looked into. So this contingency is looking at the generator trip events. So as you can see, we have simulated 3 different generator trips, but I will go through only the first one. So when we have tripped a 5 megawatt generator before the BESS, we see that we had the load shedding again from our protection system to sustain the frequency within allowable limits. And frequency nadir is actually a technical term that is related to the minimum frequency that happened after the contingency. So let's see what happened after we integrated the BESS. So again, because BESS can provide a prompt response, it has avoided load shedding. So load shedding has moved to be 0. And also it, because of the prompt response from BESS, it has also reduced the frequency excursion significantly and avoid the load shedding. So another objective that we can see, or another benefits from BESS other than reducing frequency excursion or avoid load shedding in these events, that is that the BESS didn't trip during these events. So if the BESS would trip during these events, it actually would make this case more severe. but the technology has frequency rights through capabilities and voltage rights through capabilities, so it will not trip during this contingency and will not make the case more severe, but provide frequency support and voltage support to stabilize the grid and actually make the grid more resilient. Okay, so we have discussed many topics here, Pablo and I. We have covered multiple topics from our technology, the reference projects from Hitachi ABB. We digged into measured operational data from our Porto Santo project through our customer EM, and I also discussed the business case for an island utility and also a power system study or dynamic analysis that we did for a hypothetical island. So back to you, Pablo. So can you summarize what were the key takeaways from this webinar for our audience that can leave this webinar and think about these key takeaways?
Of course, thanks, Hamide. So as I said at the beginning, and then I think hopefully demonstrated throughout the presentation, the key takeaways that we can take home today are, on the one hand, that with the grid edge solutions, in particular battery energy storage system, but also automation control and software on top, we're able to maximize fuel savings while maximizing renewable energy integration. So sometimes those two might look like a challenge. More renewables means more intermittency, but they bring the fuel savings, and we can put both together while ensuring power quality, as seen on the second bullet point, while through the deployment of battery energy storage system. These might also be the case, the power quality need in the absence of renewables, as well as we saw in some cases through some industrial activity, we might have power quality issues that we can solve and at the same time get ourselves ready for a renewable energy future. So that is another takeaway that I would definitely recommend to take home. So in the absence of renewables, there's potentially a very good opportunity as well for the deployment of grid edge solutions. And obviously, at the end of the day, as we saw, also related to policy in many cases and regulation, renewables are unstoppable. They will reach each and every island in the world. So sooner or later, the goals will be there. So ensuring that ability to integrate renewables in a fast way as well, given that renewables have a fast deployment time and very often can be installed in a short time frame, at least in terms of power generation projects. They are obviously one of the key investments that a utility could make today. So a combination of solving power quality issues and ensuring grid stability, integrating renewables, reducing cost of electricity. These are the main key takeaways. And I would say that the main conclusion is this is not something that can be done. It's something that is being done. So we have shown that this is already being the case in many different places around the world.
Thank you very much, Pablo, for summarizing the points that were talked about in this webinar, and Hamide, for your presentation. I think, well, we have quite a few questions that have come through, and I believe that we still have one more poll question, which Manuel will share with you shortly. So here we go. So what can be done to further improve the industry's understanding of the grid forming inverter technology and its applications? So you have the options are webinars like this one, simulation models and collaborative studies, publications / white papers, or a pilot project in my area. Okay, well, let's give it a few more seconds, and then we'll get some of the questions answered. I can see quite a lot of technical questions, but also questions regarding the economics of these systems. So the voting is still evolving, right? So we're gonna close in 5 seconds. There we go. Well, before that, it seems. So right. So well, the option that has been with 46/69 simulation models and collaborative studies is what could be done according to the audience to further the understanding of grid forming inverter technology and its applications. So right, so we'll stop the poll now, and we'll go straight to the questions and answers. So I think, well, there is one. We'll start with a question that has got the most votes, which is by Akhtar Hussain Javid, and he asks, what is the difference in technology for battery energy storage systems used for renewable support, such as peak shaving, valley filling applications, and one for frequency and stability? Can the same battery with higher megawatt hours be used?
Maybe I can answer that question. So in principle, the same technology, if we think, for instance, of lithium-ion batteries, can perform all these functionalities that we described. So the peak shaving, the frequency regulation support. What might differ is, on the one hand, the sizing of the system. So we wouldn't size the same way if we were performing one application or the other. And also within battery technology, and even within the same manufacturer and the same technology, there's differences in terms of whether we would be using a power platform or an energy platform, depending on the C rating of the system. So these would indeed be slightly different solutions, but conceptually it would be the same approach, same solution on the front end, and it would be more a matter of sizing and properly sizing than anything else, or choosing different chemistries. Hopefully that answers the question.
Okay, thank you. Thank you very much. And there is a question addressed at Hamida, which is how does your solar solution integrate with other optimization software applications?
Yeah, sure. So actually, that's a very interesting question, and we already have a project that we have integrated our image solution with the network manager, which is another control layer on top of the island for controlling different assets of the island, and provide network manager and distributed generation for the whole island. And both solutions are related to Hitachi ABB power grids. And the slide that I showed for the Porto Santo, the first 24-hour, the first slide was actually from the data acquisition through the network manager that was on top of this BESS solution.
Right. Thank you. Thank you very much, Hamida. And there are a lot of questions related to the use of renewable energy in islands, and one of them is how much renewable energy could you have in an island without, in a microgrid, without the need for a battery?
Mm-hmm. Yeah, that's an interesting question, and usually through our analysis and studies, we try to address that. For example, some of our customers come to us because they had installed renewables, but their diesel generators are suffering from compensating all those high ramp rates and frequency fluctuation caused by those renewables. So answering to that question really depends on looking at the case, looking at the island, and looking at what assets are available, what are the challenges for the island without BESS. And usually they will end up in power quality issues, and also end up in curtailing their renewables to sustain the frequency within allowable limits. So BESS will help the renewable investment to avoid curtailment and also improve power quality and ramp rates. So it really depends on a study and each case.
And if I may, I would add, Hamida, to that exactly what you said. So some years ago, we tried to come up with a number that would be applicable to answer this question. And what we concluded is there's too many variables, like Hamida mentioned. How are your generators, the existing ones? How are they able to respond to events? But also, for instance, the same 2 megawatts of PV, to pick an example, in a desert area, which has a very stable solar resource throughout the day, does not provide the same intermittency as the same 2 megawatt hours on an island that has clouds coming and going by all the time. So there's much more intermittency and instability coming from the variable solution, let's say in that cloudy area. And that drives a lot of the instabilities that are solved and compensated by a battery. So the penetration level is not only defined by the amount of renewables, but also about the conditions around them, because that is actually what the battery tries to solve. So very difficult to give a number that applies everywhere and anytime. We've come to the conclusion that it really depends on 4 or 5 different factors that drive that number. But in any case, what is clear is that it's very difficult, if not impossible, to bring that number to a high level without the use of technologies like the ones we discussed today.
And regarding the how you, I suppose that for you to be able to advise and provide a whole solution that includes renewable energy, you need to measure the resource on site. So how do you do that? You use satellite data to measure the wind resource and the solar resource available at that location, or how does it normally work?
So typically there's a number of publicly available data in many different locations that provide weather resource, including wind speeds and obviously horizontal radiation in the case of solar. And those are generally good enough for the good approximation of a business case and a simulation and sizing. When it comes to some particular industries like wind, for instance, there's typically a need also related to financing of projects that typically require some actual measured data on that site. So that is something that could be required project by project. But in principle, data coming from certain sources, some of which use satellite data, is sufficient in terms of quality and quantity to address the types of studies, simulations, and sizings that we have discussed today.
And one thing I think is we're coming towards the end of the time, so this is probably one of the last questions. But I wanted to ask you, I mean, right now we have seen massive volatility in terms of fuel prices, which are one of the main factors that you take into account when deciding whether to go for one of these systems or not. It seems that now food prices are low, but do you take into account volatility when you calculate these payback times? And
Yeah, sure. So that's actually one of the factors, the diesel or any fuel price that could be pricey in remote communities because of also the additional transportation costs. So we definitely look at different scenarios for the future, that what will happen, how does the investment looks like if we have reduction in the fuel cost or also increase in the fuel cost. So that's definitely one of the factors, and we consider volatility in different sensitivity analysis.
Because anyone looking well at the price of fossil fuels today might think, well, why should I consider this? But as it has gone down very quickly, could come back up. So I suppose these systems could act as a hedge against this volatility. So you never know what's going to happen in next year or in the next 6 months. So well, I mean, we have a lot of questions here, and a lot of questions are related to actually this business model, the cases. So, if you have something, I can see that one of your colleagues has shared a document there. So hopefully, there are some of these business models and their assumptions there. So everyone in the audience can see them with more at leisure. So you don't have to hurry now. And I think what we will do is that we'll send you the questions that have been asked, and then so you can answer them on a one-to-one basis. Because I'm afraid that as all good things, this webinar must also come to an end. So
I think it's important to emphasize what you said, Carlos. So we'll be happy to go through all the questions since we didn't have time to address all of those today, and share them along with the materials. So I think it's important to address those questions that came up. So we'll be happily ready to do that.
Great. Well, I'd like to thank everyone in the audience who has been here today with us, and I'd like to thank you, Hamide and Pablo, for your presentations. Very, very interesting. And remember that we will send you the recording of this webinar and the slides as well, and you'll be able to get an answer to your questions from Pablo and from Hamide. So once again, thank you very much, and well, have a great day.
Sure. Thank you.
Thank you, Carlos.
Thank you.
Thanks.
Bye.
Take care. Bye.